Hello chaps and chapettes. Now we're going to continue looking at different types of circuits today by looking at parallel circuits. As you can see, it's a lovely sunny day outside, which is why I'm hiding inside to do some physics. So let's get on with what we need to do. We need to know what a parallel circuit actually is. We need to understand how current and resistors and voltage behave in parallel circuits, and we need to be able to draw a parallel circuit as well. If you've watched the previous video, this is exactly the same as what you did for the series, but now we're going to be doing a different type of circuit. The challenge today is actually a big one. See if you can do any redstone parallel circuits in Minecraft. It's actually more tricky than you might think, and I look forward to seeing what you can do and in the comment section below. So let's jump straight into what we need to look at. We need to know that parallel circuits are arranged differently to series circuits, and they're aligned next to each other with literal parallel wires connecting up each component. They look kind of like a ladder if you were to stack them all on top of each other. And that means that the electricity behaves in a very funny way. And rather than talk about it here, I'm going to show you on my whiteboard at the back of the classroom. So on the way there, make sure you hit the like button so that the YouTube algorithm knows I'm here and that more people can find this out. It really does help the channel. And join me at the back. So exactly the same setup this time as we had with the series circuit. We're now going to look at how to make a parallel circuit. For that, we're using our trusty battery pack, and we're going to use some light bulbs. But this time, we're going to arrange them in a sort of a ladder formation, like so. Now this is going to make me very happy because I can use the exact right color for all the wires on this one. All the black holes lining up with black wires, like so. There we go. And all the red wires lining up with the red wires, or red holes, like so. And boom, there we go. Now you can see straight away, if you just come from the series video, that the light bulbs are much brighter than they otherwise would be. And I'm just going to disconnect this one now. You can see the brightness of that first light bulb doesn't change. If I add it in, they both have the same brightness. And that's going to be referring to the amount of voltage that's being dropped across them. So I'm going to leave that there for a second. Okay. So you can go back and then we'll have a quick discussion about what we need to do in terms of voltage, current and resistance. But there you go, parallel circuit. So you just keep adding things in a nice long ladder all the way down with your one side of your components all lined up to the 0 volt side of your battery and the other side all lined up to the positive voltage or negative voltage, actually doesn't matter, to the other voltage of your battery. And well, there you go. So now we need to think about how resistance and how voltage and how current behaves in a parallel circuit. And it's weird. It's not as straightforward as the series circuit. So we need to go through it in a lot more detail. And of course that means we're going to do it at the back of the classroom. So hit the like button on the way, join me at the back. Right, now what we need to do first is look at the voltage of this one, because the voltage is the easier one to understand. So I've got my multimeter here and it's set to voltage already. So setting to voltage. Okay, just plug that in. And you can probably guess what's going to happen with this one. If we measure the voltage, I'll put that there actually, you can see it. If we measure the voltage across the battery, there we go, we end up with 5.7 volts. Not quite 6, but 5.7 is good enough. There we go, 5.7 volts. And if we measure the voltage across that one there, we get 5.7 volts. And if we measure the voltage across this light bulb, you get 5.7 volts. And that's actually kind of obvious, really, because we're not going down any steps in terms of potential difference. We start off with 6 volts on this side of a wire, and because these wires are all effectively connected up to the 6 volt part of the battery, all these wires must have a potential difference of 6 volts, as in there must be 6 volts on this side of our circuit. All the wires on this side are connected up to the 0 volts, which means that when an electron gets to this side of the circuit, it must have 0 volts. Makes sense, right? So going from here to here, we need to have a potential difference of 6 volts, going from 6 to 0 down there. Now, if the electron chooses to go through this part of the circuit, through this component, it goes from 6 down to 0, so 6 volts. If it goes through this wire and goes from this part down to this part, then it must go from 6 to 0, 6 volts. So that's why, if you stack things up in parallel circuits, you'll get the same voltage across every single one. Now don't take my word for this one. What we're going to do is hook this one up. Do I have enough battery? Yeah, here we go. And you can see that the brightness of those light bulbs will stay the same, because they're still getting 6 volts dropped across each one. Now this is kind of dangerous because something happens to the current, but we'll talk about that in a second. This is why, though, most of your home appliances and your home electrical grids and your light bulbs and your lighting fixtures will be arrayed in parallel, because then you get the same voltage being dropped across all of them. So they're all going to have the same sort of the same brightness value. Can you imagine if you put these things in series? As soon as you plug in like one more light bulb, all the other light bulbs will get dimmer. And to keep doing it, then your light bulbs will get dimmer and dimmer and dimmer, and you'll have like a cap on the number of light bulbs you can put inside your house. This way, you kind of still have a limit, but not as hard a limit as you would with a series circuit. Now there is something that goes wrong with current on this one. For that reason, I'm just going to take this out, because I don't want this thing to burn out on me. Ow. Okay. Getting quite hot already. So, there we go. What we need to do now is we need to look at how current is going to be here and here on the circuit here. So, let's just plug in, actually we need to keep that connected up. If we plug in our multimeter now into ammeter mode, there we go, we see that we have a negative number again. I don't know why I never connect this up properly. Hang on a second. There we go. Don't like negative numbers. We have a current of 0.6 amps, roughly speaking. Okay. Now what we're going to do is we're just going to disconnect this thing. Okay. Remembering that that was 6 amps up there. Disconnect. There we go. And we're going to plug the ammeter into this one. Guarantee that this number is going to be negative now. Guarantee it. Absolutely guarantee it. It's going to be, yeah, it's negative. But you can see the value's also changed. We've gone from 0.6 amps down to 0.3 amps. We're just rounding up for this one. And that means that the current has actually split. Now it's a little bit difficult to see on this particular setup. So actually what we're going to do is we're just going to adjust this now so you can see what it might be like otherwise. So what we're going to do is we're just going to keep this set up here. Okay. So now we have some of the current going through this one and some current going through this one. It's basically the same circuit. If we're doing the voltage, we'd still have 6 volts being dropped across here, 6 volts being dropped across here. But now what we're doing is we're splitting the current. And if we put a multimeter in there, set to ammeter mode, then we can see that we actually get 0.3 amps of current going through. So 0.3 amps, 0.3 amps. This is what happens to current in a parallel circuit. It actually splits from branch to branch, going all the way down. And that's one of the rules. If you think about the series circuit, in that one, it's going to be splitting the voltage as it goes across each component. In a parallel circuit, it splits the current going across them. So they're kind of the mirror opposite of each other. And that's how that works. What this does lead to is some slight problems. If you keep stacking component after component after component of this, you're actually going to start increasing the current that flows through. And there's a reason for that. It's because the resistance goes down. And, well, it gets a bit complicated from that point on. Do you remember how when we were looking at the resistance of, actually just disconnect that so it's not wasting energy. There we go. When we were looking at the resistance of, well, resistance, if you had, there we go, a nice wide substance, then the resistance would be quite low. If you had a thin substance, then the resistance would be quite low. And as we start adding things in parallel, it's almost like we are making a wider surface area So we can go from a low resistance thing, just being one of them, to, a high resistance one to a low resistance one, because we're effectively adding surface area, which means that as we add more components on this one, resistance actually goes down. And because resistance is going down, and because the voltage is staying the same, the current is going up. This is why you can actually trip your circuits at home. If you keep adding appliances and light bulbs and things like that to your home grid, then eventually the current goes up and up and up, and that's when you can start causing problems like fires and things. And that's when you can trip your fuses, trip your circuit breakers. And I've got another video on that in the description below, and well, there you go. So, as we start adding more components, the resistance of all those components goes down, and the current, which is going through the whole circuit, is going to go up. So when we do the actual circuit diagram, I'll show you the maths behind that, and just so you can remember it more cleanly. Okay, now we've looked at how these things behave, but now we need to look at how we can draw a parallel circuit. We've been doing that pretty much the entire of the video, but just to make sure it's secure in your head, let's go through the steps of how you draw a parallel circuit and how you can show the examiner you know what a parallel circuit is. So, without further ado, hit the like button if you haven't done so already. Come and join me in the back. Let's just turn those off. There we go. Okay, so for the parallel circuit, it's very easy and straightforward to draw. Oh, good. Switch that around. I think I need to get a new black pen. Let's do the components first, actually. There we go. Components. And then put the wires in second. There we go. And there we go. So these are going to be, this is going to be a parallel circuit. And it's quite obviously a parallel circuit. We've got more than one component, and they're stacked up on top of each other. You know, just looking at this thing, I think it's the wrong way around from what we were doing before. Let's just make it the right way around. There we go. There. Okay, so in terms of the voltage that goes through this thing, if we start off with, let's use red for voltage, 6 volts on this side, 0 volts on this side, that means that the voltage dropped across there. So V1 is going to be 6 volts. The voltage dropped across there. V2 is going to be 6 volts. Okay? So what we can say is, put that VT. What we can say is VT is equal to V1, which is equal to V2, and they're all going to be the same. Okay, so the voltage is the same. Now what we can do in terms of current, actually let's use green for current. I think current's more green than anything else. So we have current here, and we have, let's just say 2 amps of current. Well, hang on. Let's use 4 amps of current here. We have 4 amps of current here, then half the current is going to go that way, and half the current is going to go that way. So we end up with 2 amps there, and 2 amps going that way. Basically, as long as the resistance of these things is the same, you're going to get the same number of electrons choosing to go that way as that way. If this one's going to be higher resistance, then most of the electrons will kind of choose to go this way. It's just easier for them to go through, and electrons are inherently lazy, so they choose the easiest path, or the path of least resistance. On the other side, we still have 2 amps here, and 2 amps here, but then they will combine together to form 4 amps on the other side. Okay? So there we go. That's got a split. I can't really do a nice neat formula for that one, because it doesn't really apply that well. I could say that I total is going to equal to I1 plus I2, but then it gets a little bit confusing because where's I1 and where's I2 and all that kind of stuff. So don't really think about it in that way. Think about it in terms of current being split amongst the components instead. However, we do need to think about the resistance, and resistance I'm going to do in purple. If the resistance of this is R1, and the resistance is R2, then we actually need a formula which allows our resistance to go down the more we add to it. There's 2 ways to do it. I'm just going to show you the one which is the easiest one. Now this is the formula. 1 over RT is equal to 1 over R1 plus 1 over R2, and then you can just keep adding them afterwards, okay? This is the easiest one to remember because it's just 1 over and 1 over and 1 over, and you just add them all together. Now the important thing is to remember to, at the end of the actual formula, to flip this around again by making everything 1 divided by your total over there, and then that's going to give you your total resistance. If you end up with a larger resistance than any of your components here, something's gone wrong. You need to stop, go back and try again. But there you go, that's the idea. There's a lot to take in here. So make sure that you're pausing regularly on the video, you're writing things down, you're drawing things out, you're actually engaging with it. If you're just sitting there listening passively, it's not going to go in. You actually need to sit there and draw these things out. Even better if you can get a piece of computer software which will allow you to play with these things. But make sure you're actually engaging with it by drawing things out or writing things down. Otherwise, it's not going to work. You're just not going to do effective studying. So, with that in mind, this is an important formula, and this is an important bit of understanding, and this is an important bit of understanding. Make sure you can write that down and use it, and make sure that you can do exam questions with it. I mean, I think this is about the most difficult one you can do in GCSE, so at least in terms of resistance and things. However, I do have another video on how to combine resistance in series and parallel. If you're really stuck on it, go back, have a look at those videos. They should help you out. I'll put the link in the description below. All right, guys, let's go back to the front of the classroom and talk about some other bits. And there we go. That's really all it is to a parallel circuit. So I hope this was very useful to you. What you should now know is what a parallel circuit actually is, and you should be able to understand how current, resistance, and voltage behave in a parallel circuit. It's a bit strange, but if you don't get a bit confused by it, go and rewatch those parts of the video. And if you really are stuck, just write a question in the comment section below. You should be able to draw a parallel circuit. If you can draw a circuit already, nice and straightforward, but it is required by the exam boards. The challenge today is to try and do some parallel redstone, and I'm really curious to see what you guys come up with. I mean, I play Minecraft quite a bit. I can't say that I've actually done a lot of redstone engineering, but you can apply most of the physics things that you learn in GCSE to building redstone contraptions in Minecraft and making the logic circuits and things work out well. So I'm kind of curious to see what you guys come up with. So let me know in the comment section below. Now be sure that you subscribe if you haven't done so already, so that you know where to find these videos when you're doing your next piece of homework or next piece of revision. And make sure that you hit the notification bell so that you can get the up-to-date videos for all the different Star Wars or food physics videos we do, and also if there's any bits of news about exam board information that you need to find out about straight away. So guys, I will see you in the next video. Have a really good day.